I said this conics topic was like an extension from parametrics with the parabola. So let's have a look at the parametric form of the conics. First of all, our circle, so there it is, x squared plus y squared is a squared. The way we define the parameter is actually to do with the angle it makes at the center. So if I join the point up on the circle, and that angle being the angle it makes with the positive part of the x-axis, then I can define the x and the y value in terms of one number, that being the angle. Radius, of course, is constant. So the x value, well, x over a would be cos theta, so x would be a cos theta. And the y value, we get a sine theta. So the parametrics for the circle, a cos theta, a sine theta, theta being the parameter. So the angle that it makes there at the center. The proof, well, all I've got to do is substitute that into x squared plus y squared, I guess. So in the two parameters, we get a squared cos squared plus a squared sine squared. Cos squared plus sine squared is 1, so yes, indeed, those parametrics work. Let's move on to the ellipse then. There's our random point. I'm going to draw in that auxiliary circle that I did the other day. Now, the mistake that is often made with the ellipse, when we say what's the parameter, it's not like the circle where we just join P up to the center. Okay? The way we get the angle for the parameter is like so. From the point P, if I go vertically up to the auxiliary circle, then that point I join to the center. That is the angle I want for the parameter. So x, just like with the circle, becomes a cos theta. Now, what happens with this, the y value, if I was to draw in the smaller circle with the radius of b and go horizontally from that point, it happens to intersect on that hypotenuse. And so I can use the smaller circle to find the y coordinate. And so y over b will be sine theta, so we get b sine theta. So it's very similar to the circle's parametrics. It's just that the radius is not consistent. So for the x value, we use the, in our picture, major semi-axis, and for the y value, we use the minor semi-axis. But as I say, the parameter is not when you join P up to the center. It's when you join, well, either way of looking at it, either you get the point and go vertically up to the large circle, or horizontally across to the smaller circle, where that point joins the center. And again, the proof, I can just substitute into x squared on a squared plus y squared on b squared, and we see that, oh yes, indeed, that does come up with 1. I mean, theoretically, you could have a sine theta, b cos theta, but theta would not be referring to that angle then. Which angle would it be referring to? Yeah, be this one in here or that one up there, whichever way you thought. I mean, they're the same angle, of course, alternate angles. So we tend to go with the a cos theta, the b sine theta. Then it sticks with that idea of the angle with the positive x-axis. All right, let's find the equation of the tangent and the normal to an ellipse. Because you'll remember in parametrics, we often finding these lines, tangents, normals, and what have you. So x squared on a squared plus y squared on b squared is equal to 1. Now, if I want to find the tangent, I've got to differentiate. I'm going to do it implicitly rather than making y the subject. It's going to be quicker. So we get 2x on a squared plus 2y on b squared, dy dx, and differentiate 1, you get 0. Rearranging that, that's just reminding us, implicit differentiation, chain rule, rates of change, call it whatever you like. It's all the same idea. And there's our derivative, minus b squared on x on a squared y. So to find the derivative, we need to substitute in both the x and the y value. And that's because we're dealing with something that's not a function. If I was to substitute in the x value, well, which point am I talking about? The one on the top or the one down the bottom? So depending on which point, I would have a different slope. So I need to substitute in the y value as well. At the point x1, y1, if we used Cartesian coordinates, the derivative then is minus b squared x1 on a squared y1. So tangent, point slope formula, look at that, get rid of the fraction, Well, I'm going to tidy this up a bit. Now, what I've done there is I've divided everything by a squared b squared. Now, the right-hand side can be simplified. Anyone see what the right-hand side is? Y. So x1, y1 is actually on that ellipse, therefore x1 squared on a squared plus y1 squared on b squared is equal to 1. We come up with an equation which is quite nice. The equation of the tangent looks like the equation of the ellipse. Right? The equation of the ellipse is x squared on a squared plus y squared on b squared is 1. We've got x times x. Okay, one's a pronumeral, one's a constant. But you can think of x times x like x squared. And then the y1y, you can think of that like y squared. So it has that same form as the equation of the ellipse itself. The normal, so negative inverse a squared y1 on b squared x1. This time, let's divide everything by x1, y1. It's not quite as neat as the tangent one, but actually there is something there that can be simplified. Can anyone see it? A squared minus b squared can be simplified. A squared, e squared. Remember when I wrote it in a fraction form, I said e squared was equal to a squared minus b squared over a squared. Well, if you multiply by a squared, you get a squared, e squared is a squared minus b squared. So is that a little bit neater? I suppose it doesn't really matter. But that changing from a squared minus b squared to a squared, e squared, I think it looks a little bit neater anyway. But other than that, it is what it is. There's our general form of a normal. Let's have a look at the parametric form. So I'm going to, instead of using x1, y1, use a cos theta, b sine theta. So my derivative becomes minus b cos theta on a sine theta. Avoid the temptation. Don't change that to cot theta. Leave it as cos on sine. Okay, tangents. The reason we leave it as cos on sine is so now when I get rid of this fraction, I'm going to have an AB sine squared on one side and an AB cos squared on the other side, which I can join together. And of course, sine squared plus cos squared is 1. Okay. So there it is in parametric form. X cos theta over A, Y sine theta over B is equal to 1. So what happens to our normal? This time, there's that a squared minus b squared. It's times sine theta cos theta this time. So let's divide by the sine theta cos theta. And there we go. We get ax cos theta minus by sine theta is a squared minus b squared, which of course is a squared e squared. Okay, so to summarise that, there's our ellipse. Equation of the tangent in Cartesian form. Equation of the normal in Cartesian form. Tangent in parametric form. And the normal in parametric form. Simply find the equation of the tangent. So whilst we spend all that time looking at that, it's no different to any other question that we've done before. I suppose the only difference here is I need to differentiate implicitly to get my derivative. Well, I don't have to, but it saves a heck of a lot of time rather than trying to make y the subject. So x squared on 16 plus y squared. Well, x squared on 16 becomes x on 8. Y squared is 2y divided dx. And of course, differentiate 1, you get 0. So rearranging that, dy dx is minus x on 16y. So for our point, the slope will be 1 on 4 root 3. Point slope formula. Bingo. There's the equation of the tangent. So I'm saying, we don't need to worry about memorising a formula when the process we know. So it's just as easy to do the process. Let's find the equation of the normal to the ellipse. So this is, I guess, what you were talking about just before. Let's imagine in this question we haven't already found dy dx and we've just got the parametric coordinates. Now a reminder, differentiate sine, you get cosine. Differentiate cosine, you get negative sine. So I'll find dx to theta, minus 2 sine theta. Dy to theta, cos theta. So therefore, dy dx ends up being cos theta over minus 2 sine theta. So there's my slope. Now we want to know at the point where theta is pi on 6, so sub that in, we get minus root 3 on 2. Point slope formula, and there's our equation. Now, in case you're wondering the x and the y values, how I got them, go back to the original question. They've told me x is 2 cos theta and theta is pi on 6. So I just sub theta in to work out which point we're talking about. Let's look at something a bit more interesting. Now, they've told us y equals mx plus k is a tangent to the standard ellipse. Now, if that's true, we're going to prove that a squared m squared plus b squared is k squared. Okay, I'm going to do it in parametric form. So x is a cos theta, dx of theta is minus a sine theta, dy to theta b cos theta. So my derivative is minus b cos theta on a sine theta. Now, if y equals mx plus k is a tangent, the slope of the tangent is m, so the derivative should equal m. So I know that m is minus b cos theta on a sine theta. So I know that to be a fact. Playing around with that one, get rid of the fraction, moving everything to one side, I've got the relationship am sine theta plus b cos theta is 0. Okay. But the other thing I know is the tangent meets the ellipse at that point I'm playing with, a cos theta, b sine theta. In other words, a cos theta, b sine theta, not only is it on the ellipse, it must be a point on the tangent as well. So if I substitute that into the equation of the tangent, y, b sine theta, is equal to mx am cos theta plus k. And playing around with that one, I get am cos theta minus b sine theta is negative k. I've got two equations. Well, if I square the first one, I'll get a squared m squared sine squared plus 2ab m sine theta cos theta plus b squared cos squared is 0. If I square the second one, a squared m squared cos squared minus 2ab m sine theta cos theta plus b squared sine squared is k squared. Add them together, the middle term will cancel, and I have a squared m squared sine squared plus cos squared plus b squared sine squared plus cos squared is equal to k squared. Sine squared plus cos squared is, of course, said with such enthusiasm. And there we go, we get our result. A squared m squared plus b squared is k squared.
For this question, is there like a way to like derive like a quadratic equation that do the discriminant?
Yeah, sure. I mean, like there's all sorts of ideas we could use. Because yes, you could say, well, I want to solve the equation of line simultaneously with the equation of ellipse. That'll create a quadratic. If it's a tangent, the discriminant is equal to 0. So yeah, you could play around with that idea. The chord of contact. Now you may remember the chord of contact question from the parabola. And I showed you a couple of ways of doing it. One was quite long, one was very quick. If we use the idea of the very quick one here, it's going to be extraordinarily quick. From that external point, just like with a circle, just like with a parabola, any conic really, I can draw two tangents to that shape from the point T. Let's say one of the tangents meets at the point x1, y1. So it would have the equation x1x on a squared plus y1y on b squared is equal to 1. No, I probably wouldn't derive that in this question, unless they specifically asked me to. Tangent at Q, let's say it meets at x2, y2, would have the equation x2x on a squared plus y2y on b squared is equal to 1. Now, T lies on both of those lines. So therefore, if I substitute the coordinates of T into each of those lines, I must have true statements. So it is true that x1 x0 on a squared plus y1 y0 on b squared is equal to 1. It is also true x2 x0 on a squared plus y2 y0 on b squared is equal to 1. They're both true. I'm looking for the equation of the line that joins P and Q. Oh, well, there's my equation. I'm looking for an equation of a line. A constant times x plus a constant times y plus a constant is equal to 0. That will be in general form. Well, x naught, remember, is that fixed point t. X naught is a constant. So x naught on a squared times x is a constant times x. Y naught is constant. Again, it's from that fixed point of t. So y naught on b squared is a constant. I've got a constant times y. That is an equation of a line. x1, y1 lies on that line because we know, let's just go back to it there, that x1, x naught on a squared plus y1, y naught on b squared equals 1. So I know that when I substitute in x1, y1, it equals 1. I also know that when I substitute in x2, y2, it equals 1. So that must be the equation of the line. But again, it has the feel of the equation of the ellipse. The equation of the ellipse, the equation of the tangent, the equation of the chord of contact, they all have that same structure to it. All right, time to play.